All right, let's figure out, the first thing to do is to figure out how many neutrons. The masses, you can't look them up because they're not in the table you have, so I'll give them to you, right? Let's figure out how many neutrons, though, are released. So the top numbers, if we add it up, we've got a total of 236 nucleons here, 235 plus 1, right? And then here we've got 138 and 92. That's 230 here. So how many neutrons? Well, 230 plus 6 makes 236, right? So it's 6 neutrons, right? That's how many neutrons, right? And that's a lot. The typical reaction you'll see is, that maybe it releases 3 neutrons, but this could happen, right? I'm sure that all manner of nuclear fission reactions occur in an explosion or in a nuclear power plant. Okay, so now what we need to do is figure out the energy released, and we'll do that by figuring out the mass defect of this, right? So the mass of uranium-235 is 235.043. That's a 0. 932. Plus, and then a neutron is 1.008665. And then that turns into cesium-138. And by the way, all these things are radioactive. That's radioactive. It's got way too many neutrons. That has way too many neutrons. We're venting neutrons here, right? This huge elements like this have way more neutrons per proton than these guys should have, right? But anyway, cesium-138 has a mass of, and they're all down here, right? 137.911011 plus rubidium 91.919725, right? And I looked these up on the online table of nuclei. Back in the day, there was we had a book that we had to look them up in. Okay, the book. All right, and then plus 6, 1.008665. And this mass is in your data packet. I'll give it to you on the test. You have an undeniable right to that mass. All right, so let's add up the left side mass. Okay, 235.043, even though it doesn't look like a 0. 932 plus 1.008665. And that is, this total mass on this left side is 236.052597. Let's look at the right side mass here. It's going to be less. 137.911011 plus 91.919725. All right, plus 6 neutrons. So 6 times 1.008665. And I get the mass on the right side is 235.82726. These are all atomic mass units, right? So the change in mass is that the mass decreases by 0.169871 U. Now you have to say, well, where did that mass go? Where did it go? Okay, it turned into energy, right? So the energy released, we're going to multiply by 931.5. This is definitely a positive Q value, okay? So times 931.5 is 158.2 MeV, right? Now, the reason this is positive is that we're losing mass, right? So where did the mass go? The mass went into energy released. In fact, on this side, you could say plus 158.2 MeV. That would make it balance out. Then you wouldn't lose any mass at all. Both sides would be balanced, right? So this is, the Q value is positive, right? 158.2. And that's a lot. 158 million electron volts of energy lost, would compare to an ordinary chemical reaction would be on the order of tens of just regular electron volts. Not MeV, but just electron volts, okay? So, yeah. And these things are radioactively unstable. These things are going to give off all kinds of gamma rays and beta rays to try to decrease the number of neutrons, right? And the neutrons spewed off also would be highly damaging radiation. Okay, so you don't want to be anywhere near this side of the equation, right? Just stay away, right? And this is what they're storing. This is what's stored in Hanford, right? Stuff like this, right? So, all right.